So the question now, where to draw shear force diagram and bending moment diagram. Here I show you the result that we obtain. And at the same time, I show to you here the coordinate axis, like we are drawing a graph here. So this is pointing, this is the axis of the member, axis of the member, axis of the member. And if we consider this as x, then we draw another axis, which is y here. So this is like drawing a graph, okay? And if positive, then we draw on this side. If negative, then we draw on this. If positive, then we draw on the positive side where the arrow is pointing. If not, then we draw on the negative side. Okay? So that is the basis here. Okay? So bending moment diagram is drawn on the compression side. So bending moment diagram is drawn on the compression side. This is our types of bending moment diagram that we draw. So when bending moment diagram appears here, means this side of the member is a compression. Bending moment drawn here means this top part is in compression, bottom part is in tension. Okay. Now, axis for plotting Q, S, and M. So we have to start indicating the axis first, axis of the member first as X, and the other axis, which is perpendicular to X. I'm showing you now my finger. I don't know whether you can see my finger now. Okay. I cannot see myself. Okay. This is a X, this is a Y. Okay. So if X do like this, then this is X, this is Y. Okay. So this form an XY axis for us to draw the graph. So X, Y, X, Y. If another member going down, so X and Y. Okay. Then here, this is the positive sign convention for Q. So Q is pointing in the same direction as X. Q is pointing in the same direction as X. Okay. Then S here. S in this case is pointing opposite to Y here. S, the positive S is pointing in this case opposite to the Y-axis. A Y-axis is like this, S is pointing opposite to it, and bending moment here is counterclockwise. Counterclockwise. When it comes to here, Q is always pointing in the direction of the X-axis. And X-axis is starting from the left-hand side. We always start from the left-hand side here. The beginning part, the end part. The beginning part, the end part. So it's pointing the beginning point to the end point. And Q is always pointing in the direction of the X. Okay. And when it comes to this part here, S also is pointing in opposite direction to the positive Y-axis for this member. This X and Y is like for us to draw the graph. Okay. XY, XY. Then bending moment again is counterclockwise. This we are looking at the cases where you start from the left-hand side, you cut here, you use the section before the cut or on the left-hand side of the cut, and then you cut here, then you use the section, you use the part before the cut here. You do not use the cut on the other side. So this appears to that situations, and this refers to that situations. So when it is inclined here, then how? Same thing, X, Y, X, Y. This is a axis for plotting the diagram. Then, same thing, Q always follow X direction, Q always follow X direction, but the shear positive directions here opposite to the Y-axis, here also opposite to the Y-axis. M is counterclockwise, M is counterclockwise. So that is a sign convention for Q, S, and M. So if we have, this is, if you want to plot the shear force bending moment diagram, so we put, starting from the left-hand end, X-axis, 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 then the corresponding Y, XY pair, XY pair like this. So for this member, anything positive shear, positive bending moment, positive axial force drawn on this side. Negative drawn on the other side. The same thing applicable to all members. This is for axis for plotting of Q, S, and M. Then next I show you the positive convention, the sign convention for positive Q, positive S, positive M for each of the cut here that we do. So here, positive shear will be like this. Positive axial, positive Q always following the axis X directions. Positive Q, positive S, positive bending moment. Positive Q, positive S, positive bending moment, and so on for the rest of the member. This positive sign convention that we use when we cut through is with the understanding that when you cut through here, you use the free body diagram to the left-hand side of the cut sections, or before the cut section, not the one after the cut sections. You start from here, you cut here, you use this one, then all this thing which is appear here is the correct convention. If you want to use the other side, then all this thing is opposite. Opposite. Right? So now if you get positive bending moment, 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 meaning that this part will bend like 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 this, and so on. And if you get negative, then it means it will bend the other way around. So that is some important things regarding the sign convention and where to plot the Q, S, and M that we need to know. And once you plot the positive bending moment, what does it mean to the deformed shape of this part, as shown here. So this is how we decide where to plot. What is the positive sign conventions for Q, S, and M? And after, when you draw the bending moment, the positive bending moment means what is the meaning? Okay, what is the meaning of positive bending moment in form of how it's going to deform for that particular portion. Okay. So next, let's go to one more example, which is after we already get to know this sign convention, where to plot. So this is a simple cantilever frame, fixed here, vertical member AB, horizontal member BC, subjected to 10-meter high. This horizontally distributed UDL. And there's a point load at the end here. So get the shear bending moment axial force diagram and draw the qualitative deflected shape. So this is a simple example compared with the previous one, only two members. So statical determinacy should be able to check without any problem here. Number of reaction, number of equilibrium equation 3, so statically determinate frame. Reactions. So the first step, as I mentioned, is always in most cases, we have to calculate reaction forces. But in this example, the same like cantilever frame, cantilever beam, you do not need to calculate reaction if you start from the free end here. So that is the option that we adopt. We do not calculate the reaction force. Okay, we start from the free end. Here we need to cut twice. We need to cut twice, and this member at least once, and this member at least once. Then we proceed from C. So we cut here. So we take the free body diagram, this part. We cut here. We take the free body diagram, this part here. So we don't need this. So this is the first part, member CB here. Right? We cut here. We make use of the free body diagram. Now, I indicate here the positive sign convention. This positive sign convention is applicable to if you cut here, then you use this part here. That is the sign convention. But now we don't use, when you cut, don't use the F free body diagram to the left-hand side of the cut. We use the right-hand side of the cut because it's easier. We can use that. But remember, the sign convention for shear and sign convention for bending moment, sign convention for Q will be opposite to this one shown here. So as I indicate here, and Q I omit here because we don't need Q when you want to calculate S and M. So indicate X and Y like this. So shear is in Y direction. So this is application of equilibrium equations. Then we get shear constant, bending moment, straight line, because there is only point load. no distributed load. Next, proceed to this part here. This is so when you draw here, okay, x, y like this, okay, x and y like this. So we have shear is positive. Shear is positive, so we draw on the top part here. And bending moment is negative. Positive, we draw on the top side, and then bending moment we draw on the bottom side. If negative, then draw on the bottom side. So for this horizontal member, so this is how it looks like for this part. For this part BC. Okay, this is not a complete one yet. This is part of the structure. Okay. So go to the next portion here. Go to the next portions. So we cut here, then we make use of this part here. So this is a free body diagram. Again, shown here is if you cut here, you use the one on the before the cut section, then this is a positive S, positive Q, positive bending moment. Now we use this side, not the free body diagram at the bottom part here. So S is opposite to this as positive. M is also opposite to this as positive. And later on Q also opposite to this as positive. So this is a positive sign convention if we use this part here. So next is just try to get the shear force. I think shear force now pointing in X direction. So use this equilibrium equation. S become this 20X. Bending moment, take moment at the cut section, then consider all this loading. Then we get it to be X squared because there is a uniformly distributed load involved acting on this member now. We are calculating shear force and bending moment for this member AB now. Okay. So shear with UDL, you have a straight line, and then bending moment with UDL, uniformly distributed load, you get X squared. So we plot 20X, X starting from 0 until 10. So we get all the while positive. So positive for this member, draw on this side from 0 until 200. And for bending moment, this is with UDL, so it's a curve. So from negative 1560, curve this way until negative 1560. Okay. So the shear force and bending moment diagram that we produce, we get in with the complete one, we get to this shear force diagram, bending moment diagram. This is a complete. Now we show this is just part of it. No? It's not complete yet. So when you show the answer, you should finally show when you combine them together. When you combine them together. Axial force diagram. So we do the same thing. So axial force, positive axial force. So here from the free body diagram, we found that Q is equal to 0 because there is no other loading. The loading is acting vertically at C. There's a loading acting here vertically. There's no loading horizontally. So Q is equal to 0. Okay, so 0 here. Then the next one, we make use of this part here. So we get Q is equal to positive convention for Q. Q plus 80 is equal to 0. So Q equal to negative 80. Means it is in compression. So our sign convention here that we adopt for Q is assume that it is in tension. So if it's negative means that part of the member is in compression. So negative Q for this part AB, we have our X and Y like this. So negative drawn on the other side of this positive Y. So negative we draw on this side here. So this complete the axial force diagram. No axial force and negative constant axial force 80. Or if you use the other part here, then Q positive is like this. But if you use the other part, you need to calculate the reaction force here. Here we didn't calculate, so that's why we start from this side, because we didn't calculate the reaction force at A. Qualitative deflected shape. Qualitative deflected shape. Our bending moment diagram is drawn on the compression side. So because bending moment diagram appear on this side, so this side is in compression. This member, there's one side here, one the other side here. This side is in compression. This one bending moment diagram drawn on the compression side. it appears on the bottom part, so the bottom portion is in compression. And this angle 90 degrees must be maintained. This is fixed support, so the qualitative deflection should become like this. It should bend like this. It should bend like this, so that this side, this member, there are two sides. This side of the member become compression, so it should bend in this way. Maintain 90 degrees, and then it should bend down because the bottom part should be in compression. So that completes the qualitative deflected shape. Okay? That completes the whole part of it. The whole part of it. So we have seen several examples where the loadings are either horizontal or vertical, and the members either horizontal and vertical. Now we look at one cases where the member is inclined. The member is inclined now, class. The member is inclined. So how do we handle cases like this? So for that, we look at this example. The same example like just now, but now the member inclined. So this is still vertical, AB, 6 meter, but now this one inclined. This is 4 meter, horizontally 3 meter, vertically. And there is a load acting vertically distributed all along the members like this. And there is a point load here, 40 kilonewton. So how do we handle this? This is one of the example that we use in order to show to you how to handle a situation where you have inclined member. Remember, when you have inclined member, the way you define axial force and shear force, you must be clear on this inclined member. So statical determinacy, I think you should be able to check. And then again, if you start from C, you no need to calculate reaction force AX, AY, and MA. The two cut is needed. Cut along member A, B, C, cut along member AB. Okay. Here, we use two set of coordinate axes, X prime, Y prime, to represent the coordinate X prime pointing in the axis direction of member BC, Y prime pointing, which is vertical, perpendicular to X prime, forming one pair XY, and this one is the normal horizontal and vertical. Okay, because this one, we need this in order to define the axial force, shear force on this member. So we start with the first. We start with the first step. The first step here is when we want to deal with axial force, shear force, because they are defined perpendicular to the members. So we have to convert the distributed load first, which is acting vertically, to component which is perpendicular and parallel to the members. So this is what we do first. So this member has horizontal dimension 4, vertical dimension 3. So the length of this member becomes 5. So this gives us information about the inclination of the member. 3, 4, 5 is the inclination of the member. Okay, now we want to find the perpendicular component and vertical and perpendicular component and parallel component, and component parallel to the axis of the member. So we make use of this diagram, make use of the information about inclination of this member, and we found that if this is 10, if this angle is theta, so this angle should be also theta. Okay, so if we make use of this relationship, then we get this component perpendicular to the axis is 10 multiplied with 4/5. And this part is 10 multiplied with 3/5. Okay, that is how we take note of this conversion. Conversion of distributed load 10 kilonewton meter to component perpendicular and parallel to axis of member CB. Okay, to axis of member CB here. Okay. So this is the relationship that we need to be able to relate to. This angle and this angle, they are the same. So by taking and this length here should be coincide with this length here. So when we make use of this diagram, then we can see that this if this is 10, then this becomes 10 multiplied 4/5, and this becomes 10 multiplied 3/5 to get this component, and they are 8 kilonewton meter, and this is 6 kilonewton meter. So only the component which is perpendicular to the member will affect the shear force and bending moment. Only the component which is perpendicular to the axis of the member, in this case this one, 8 kilonewton meter, will affect the calculation of axial force and bending moment. This component here, which is parallel to the axis, will not affect the calculation of S and M. It will only affect the calculation of Q. Okay. So now, that's why we show only the 8 kilonewton meter here for us to calculate the Q and the M. So the Q, the positive Q, is indicated in these directions. Okay. And the positive shear, positive axial force is like this. So this one will not affect this because they are perpendicular, okay, and it will not affect the moment. Only this will affect the shear force and bending moment. The perpendicular, the component which is perpendicular to the axis. Okay. So with that, then we proceed to the calculation of shear force and axial force and bending moment for each of the members. So we start with member CB because we do not calculate this. So we start here, we cut here, then we take this part out as a free body diagram. So we already calculate the component perpendicular to the member. And this is at a distance X. This general represent any cross section along this member. So S, Q, and M. Q we do not show here for simplicity. We show only S and M, okay, because Q we calculate later. So we have this axis X prime and Y prime because S is not oriented, is not pointing in the vertical or horizontal direction. Now is pointing in Y prime direction, which is perpendicular to the axis of the member. So we take summation of forces in this direction of S. So the only force that we need to consider is this component perpendicular to the member, which is 8 kilonewton meter multiplied with X. So it's down and this is up. So we get S is equal to 8X, a straight line. So take note, we take equilibrium. When we want to find axial force or shear force, we take equilibrium of forces in the direction of that force. Moment at the cut section, so this is easy. So moment here is plus this moment, 8 kilonewton meter, multiplied with X, multiplied with X square. So give us the moment. So moment become negative 4X square. And this is for this member. So X is from 0 to 5 because this length of the member is 0 to 5. So class only component perpendicular to axis of member affects the shear and bending moment. So Q does not affect, which is parallel to the member. It will not affect S and M. It will only affect the component, which is parallel. The 6 kilonewton meter just now that we calculated will not affect the S and M. It will only affect the axial force. So for this part, the shear force diagram looks like this because this is from 0 to 5, all the way positive. So we draw it on the top side here for shear force positive. And the bending moment is all the way negative. So we draw on the bottom side here for this part for negative bending moment. Then we go to the second section here, B. The second section here, B. Here we can see how does this why is it curved like this? Curve like this, we can make use of the relations between slope in bending moment diagram with the shear force. So this is 0, so the slope here should be 0, and all the while positive, 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 positive shear, which means the slope increased positively. Yeah, the slope increase positively. So the meaning increase positively means like this. You know, these are positive slope, positive slope, positive slope. Correspond to positive shear force increasing from 0 until 40. That's why it has to curve like this. Or you look at the sign, the coefficient here is -4, so negative, it should curve in this way. So that completes this part only. This is part only, not yet finished. So we go to other section BB now. Other section BB. So if you, this is what I mentioned. If you take note of this, then you can know that this should be curving like this, not curving the other way around. Go to section BB. Section BB here. Then I want you to pay attention to when we consider section BB, how to deal with this. Okay. Now, previously we have to decompose this into perpendicular and parallel because we want to calculate the axial force and shear force here. That's why we have to decompose it into component perpendicular, component parallel. Now we want to calculate shear force or axial force in this member now. Okay, in this member now. So take note of that. Then, so axial force, the shear force is in the direction of x here. Let's follow our coordinate axis here. So S here is pointing like this for positive convention. Moment is pointing like this is clockwise. For cutting here, make use of this part here. Now, for shear, this is acting vertically. This is originally acting vertically because we are interested in shear in this member now. So this one, we do not have to decompose them into perpendicular and parallel. Just use as it is in the original directions. So this one is in vertical direction, does not affect the shear. So the only thing affecting the shear is this 40. So S is 40, constant, positive. Moment, take moment at cut section here. Here also, we are interested in bending moment in this member, not bending moment in this member. So we don't need to decompose this into component, perpendicular, and parallel. We use as it is, vertical directions, and moment caused by this will be 10 multiplied with this length, give you the equivalent total load here, then multiplied with the perpendicular distance to the cut section, which is the horizontal distance 4 divided by 2. So we make use of these vertical directions, no need to decompose them into parallel and perpendicular because we are not interested, we are not calculating shear force or axial force for this member. Yeah, we are calculating for this member. So that's why we do not need to use it perpendicular and parallel, but use it as it is in the vertical directions. Take note that the moment caused by this at this cut section will be 10 multiplied with the total length here to give you this equivalent force, which is here. Then multiply with perpendicular distance to the cut section, which is horizontal section, horizontal divided by 2, because this is UDL, so it's acting at the center here. So that gives us the bending moment. So simplify, we get -40x minus 100, a straight line. So shear force constant, bending moment a straight line. So to complete that, to this part, so shear force constant, positive. So for this part, we draw on this side. Bending moment, straight line, negative. So for AB, positive, we draw here, negative, we draw here. So straight line, we draw here, negative side. So combine them. Yeah, you should produce this. Don't stop here. Okay, this is not complete. This is only part by part. So to combine them, so you get our shear diagram like this, our bending moment diagram to be like this. Okay. Now, there is one particular check that you can do is at a rigid joint here, where there is no concentrated moment acting here. Your moment which you calculate for BC at this joint B here, and the moment that you calculate for AB at the same joint here, they should be the same. So from this diagram, you draw this is -100. So from this part, the diagram also -100. So they should be the same for equilibrium, unless there is a concentrated moment acting here. then they won't be the same. So this is one checking that you see whether you draw it correctly or not. Yeah, you notice here at B here, this part until -100, here also -100 until -340. So at B here they are the same. For the case where there is no concentrated moment here. Axial force. So axial force only affected by the component parallel to the members. So it's 6 kilonewton per meter we have calculated. Axial force positive convention, positive directions. So this one plus this is distributed 6 kilonewton per meter. So the total you must multiply with the x. Okay. So you get Q is equal to -6x. And after that, part AB, we make use of this part, Q positive directions. So Q is equal to, this is the only part that contribute to Q from this vertical distributed load. The total equivalent is 10 multiplied with the length 5. So Q again, we get -50 constant. Here, straight line, because there's a distributed load in the direction parallel to axis of the member. So if you plot the axial force diagram, so this is what we get. Negative, all the way negative. So for this member, y is here, so negative draw on this side. For this member, y is here, so -50 draw on this side. So changes in straight line linearly until -30, until -50, not 30. This one, -6 multiplied with 5, this should be 50. Should be 50 here. Okay. 6 multiplied with 5, 30 here, correct? 6 to -30 because 6 multiplied with 5 is -30 for this part, and for this part is 50. Now, the qualitative deflected shape, let me go to the next one, then I will stop here. Or you can use the other part. Yeah. No need to use this part, use the bottom part here, the cut section, but you need to know the reaction force. Then you get to the same conclusion that it should be -50. It should be -50. Okay. Now, qualitative deflected shape, understanding of the meaning of the bending moment diagram that we draw on the compression side, and this is a fixed support here, so A is fixed, not able to move, must at the same point, rotation must be 0. If this angle is, let's say, 120 or 130, it must maintain. So we just draw like this, maintain the angle. Then it is compression side here, so it should bend in this way, maintain angle, and then bend in this way. Okay. So that is how we complete the bending moment, the qualitative deflected shape. So bending moment diagram that we have is drawn on the compression side. Okay, so when drawn on the compression side, you have negative here, so it means it bend like this. This is negative, means it bend like this. So drawn on the compression side, so this part is in compression. This part is in compressions. Alternatively, you might get also some sources if you refer to the draw bending moment on tension side. If you draw bending moment on tension side, if this part is in tension, this part is in tension. So if you draw the bending moment diagram here, instead of here, so you get bending moment diagram on the tension side. So if you draw here instead of here, so you get bending moment diagram drawn on the tension side. So the one that we have gone through is we draw bending moment diagram on the compression side. Now, there's one point that I want to point out, I think, before I stop, okay, is when you draw shear force diagram or bending moment diagram, please take note that, let me see, okay, when you draw here, this when you draw on this particular member, this you must draw it 90 degrees, okay? The same thing here, you must draw it at 90 degrees. So the bending moment, the same thing. When you draw, make sure that this is maintained roughly as 90 degree. This is maintained as roughly 90 degree. So that is the way that we should draw. So don't draw like this, which is it will not be correct. If this part, okay, if you draw the bending moment diagram, here it should be 90 degree. So don't draw like this, which is not 90 degree to this member, or this part here you draw it like this, which is not 90 degrees, so it is not correct. So it should be drawn 90 degrees to the member. Okay? Here it should be drawn 90 degrees to the member. The same thing here, 90 degrees to this member. For this part, make sure it is 90 degrees. Okay? Like drawing a graph. The same thing for axial force diagram. So it must be drawn 90 degree perpendicular, yeah, to the. Then that is the correct way of showing that thing. So let me stop here now. It's already 10:45, so I initially want to stop at 10:30, but we started a bit late. Okay.